Okay, we're back. The next few sections are covering what are called power series. So this begins with 11.8. So here we'll introduce the concept. So first the definition. A power series is a series I suppose I should do it like this. Cn, summation of Cn times x minus a to the nth power as n goes from 0 to infinity. So this is a power series centered at a. All right, so let's consider this for a second first. Okay, so x is a variable. Cn is a sequence, so it's a function of n. Cn, the sequence. A is a fixed number. So A is the center of this power series. Okay, so a power series is basically, you can think of it as a series that involves powers of the variable x. So then, if you pick a specific x value, so you assign a value to x, this series will either converge or diverge. So it'll be either be convergent or divergent. So we can define a function f of x that equals this power series now I'm out of space to write, whose domain, so we can define this function, but it's only a function if you get an output. So you can only plug in certain x values and get outputs. So the domain for this function we've defined is the set of x values that give you a convergent series. So whose domain is the set of x values for which the series converges. For which the series converges. Hopefully you can read that. Okay. So let's do maybe the simplest example first. Okay, so let's look at a power series function. F of x equals the summation of x to the nth power. Okay, so let's write this out just while we're getting used to this. So I think of this as an infinite polynomial. So when n is 0, I get x to the 0 power. That's 1. When n is 1, I get x to the first power. When n is 2, I get x squared. When n is 3, I get x cubed. And so on. So this power series is like an infinite polynomial. It will converge to a value for certain x values. So this is convergent. This series is convergent if Well, let's just look at it. This is exactly the same series that it's the same type of series as if we had r to the n, the summation of r to the n. That's just a geometric series. So for a fixed x, this is a geometric series, and those are convergent if that ratio has absolute value less than 1. And it's divergent otherwise. Okay, so the domain for this function is the interval. Well, absolute value is less than 1 means x is between -1 and +1. So my domain would be the interval -1 to +1. Now, while we have this example here, the power series, the function on this interval, the function is given by the values this power series takes for different x values. For this example, though, we have what's called a closed formula for this function. So if this is convergent, it's a convergent power series, we have a formula for that. It's this formula. Well, it's on this fraction, the denominator is 1 minus r. In this case, r is x, so we have 1 minus x. And on the top of the fraction, we have the first term, or the initial term of our series. So when n is 0, I get x to 0, which is 1. So this power series, actually, when it's convergent, equals this function. So we'll talk more about this aspect a little bit later. But if I have a function in mind, there will frequently be what's called a power series expansion or power series representation for that function. So this function is equivalent to this power series on this domain. They represent the same function. Okay, and while I still have it here, about the center of a power series, well, this one is x to the n. That's the same thing as x minus 0 to the n. So this power series is centered at 0. The a value for this power series is 0. And so if you look at the domain here, it's an interval -1 to 1, and right in the middle of that interval is 0. So our domain will be centered at whatever the center is. We'll talk more about that a little bit later. Let's do another example where we just find the domain. So find the domain for the power series function f of x equals let's do this one. Summation from n equals 0 to infinity, and we'll do x to the n divided by n times 2 to the n. Okay, so x is a variable. We're trying to answer the question, for what values of x is this a convergent series? So what we need to do, now it's a more complicated series than the previous one. It's not just a geometric series anymore because we've got this extra n. But if we want to answer the question, when is this convergent, what we can usually do is use either the ratio test or the root test. Let's just look at it and see what happens. So I'll use the ratio test here because not everything is raised to the nth power. The n is not raised to the nth power, so I don't really want to take an nth root of it, although it wouldn't be that bad. Let's do a ratio test. It's simpler. So ratio test from the previous couple videos, we take the limit as n approaches infinity of the absolute value of the ratio of the n plus first term divided by the nth term. So the n plus first term would be x to the n plus 1 divided by n plus 1 times 2 to the n plus 1. Then we have to divide by the nth term, which is the same thing as multiplying by the reciprocal. N times 2 to the n divided by x to the n. So then we group corresponding factors to see what their limits are, see what their cancellation is. Let's just do it like this. So the x's, x to the n plus 1 divided by x to the n gives me x on the top. 2 to the n divided by 2 to the n plus 1. I have one extra 2 on the bottom, so that leaves me with a 2 on the bottom when I cancel. Then I have n divided by n plus 1. So now what's the limit of this? Well, with respect to n, x over 2 is a constant. N over n plus 1, that's a rational expression with the same degree on the top and the bottom. So the limit's just the ratio of the leading coefficients, so 1 over 1. So this is going to give me 1 times x over 2 inside absolute value, so my answer is going to be x over 2 absolute value. Right? So then you ask, well, is this convergent or divergent? Well, the ratio test tells you convergent if your limit is less than 1. And it tells you divergent if it's greater than 1. So for this to be for this to successfully tell me convergent, I need absolute value of x over 2 to be less than 1. Well, if I multiply both sides by 2, that tells me absolute value of x needs to be less than 2. Okay, so I don't want to erase everything here. I'll just erase the work for the ratio test. So what we have then is this is convergent if absolute value x is less than 2. It's divergent if absolute value x is greater than 2, because in that case, if this limit was bigger than 1, that would mean absolute value x was bigger than 2. Okay, so ratio test tells you convergent if the limit's less than 1. It tells you divergent if the limit is bigger than 1. It was inconclusive if the limit equals 1. So that means if the absolute value of x equaled 2, we wouldn't know if this is convergent or divergent. So let's think about that case. So if absolute value x equals 2, the ratio test is inconclusive. But instead, so I can't use the ratio test for that value, those values of x. So instead, let's separately check what happens to my series when I plug in x equals 2 or x equals negative 2. So if absolute value of x equals 2, that means x equals plus or minus 2. All right, so let's try to fit it in over here. Well, no. So you've got this copy down, hopefully, so I can erase it. I'll rewrite it at the end when I'm compiling my answers. Okay, so we want to check if x equals 2, then my series would become 2 to the n divided by n times 2 to the n. So then you simplify that. The 2 to the n's cancel, and I'm left with just 1 over n for my series. And now go back a few lectures. Summation of 1 over n, that's a divergent series. Either it was one of the first divergent series we looked at, or it's the p series with p equals 1, which is divergent. This is divergent, though. So if you haven't already, you want to get familiar with the simple types of series. The p series, the geometric series, know when they're convergent or divergent. So 1 over n, that's divergent. Okay, now check x equals negative 2. So we plug in x equals negative 2 to this. That gives us minus 2 parentheses to the nth power divided by n times 2 to the n. Now if we cancel, the 2 to the n cancels, but we're left with a minus 1 to the n left over on top. So this is summation of negative 1 to the n over n. That's an alternating harmonic series or alternating p series, which is convergent for p equals 1. So this is convergent. Right? So, putting this all together, it's divergent when x equals 2. It's convergent when x equals minus 2. But from what we did previously, we're trying to find the total domain where this thing is convergent. Well, we know it's convergent everywhere between minus 2 and positive 2. So it's convergent between these two. But then we had to check these two endpoints. Is it convergent or divergent? It was convergent when x equaled negative 2. So negative 2 is a part of our domain. It wasn't convergent when x equaled positive 2. So that's not part of our domain. So we get a half open, half closed interval. Within this set, it's a convergent series. Outside this set, that includes 2, it's not convergent. So our domain is this interval. And again, what is the center for this power series? Since it's just x to the n, that's x minus 0. So the center is 0. And again, our domain is centered at 0. It's a symmetrical, well, as far as the length goes, 0 is the midpoint of this domain. All right, so let me state a theorem before we do more examples. So, theorem. So, for a power series, summation from n equals 0 to infinity, Cn times x minus a to the n, it's an a, there are 3 possibilities. As far as convergence goes, or as far as the domain goes. The first possibility is the series converges only at x equals a and nowhere else. So the only x value is a. If x equals a, you have a minus a is 0. We're just adding up zeros. Right. So it's always convergent when x equals a. So this is like the worst case scenario. Next possibility is it converges everywhere. It converges everywhere for all x values. So that's kind of the best case scenario. Then any x value can be plugged in and give me a convergent series. The third possibility is there is a positive number R, capital R, called the radius of convergence. Such that the series converges on the interval a minus r to a plus r. So from here to here, the endpoints we have to check separately. So I'll put parentheses here. They could be square brackets. One or both could be square brackets. So it converges inside this interval and diverges outside it. The endpoints have to be checked separately. I'd write that down if I had more space. But the endpoints we have to check separately. But as far as the total interval goes, this tells you why A is the center. A is the center for this power series because it's the midpoint of this interval. And you go the same distance in both directions from A to get the what's called the interval of convergence. All right, so you have these three cases. The third one is the only one where well, let me say it like this. All three of these we can talk about a radius of convergence. So I only defined it in the third one. These other two cases, the radius, if it converges everywhere, the radius would be an infinite. So r equals infinity for the second case. If the series converges only at the center, you don't have a positive radius. You have to be at the center for it to converge, so the radius would be 0. So we say r equals 0 for this case. Okay? So we'll do another example here. Another couple of examples. But basically the way it works is to study a power series, to figure out where it converges and diverges, we first use the ratio test or the root test. It'll get us to the radius basically. So it'll get us to the interval of convergence, but it won't tell us the endpoints. I mean, you don't have to worry about the endpoints in these first two cases because there really aren't endpoints. You either get a radius of 0, in which case you only converge at a single point, or you get it converges everywhere, no matter what x is, in which case your domain's the entire real numbers, or it'll get you to an interval like this. Then you have to check the endpoints like we did on the previous example, and that's just going to be whatever the test is. So you plug in the specific x values at the endpoints and see what does your series turn into after you simplify it. Okay, so let's do some examples here. So I'll just write the question once, but here's the way these are phrased usually. Find the radius and interval of convergence. All right, so then you're given a series. Don't need to call it f of x each time. We've got the series summation from n equals 0 to infinity of x plus 3 to the n divided by 4 to the n. Okay, so before we do anything, let me just point out what is the center. Well, the center is the x value that makes these parentheses 0. So in this case, it would be negative 3. When x is negative 3, I just get 0 to the n. Adding that up is going to be 0. All right. Okay, so then what we do is we need to figure out the radius first, essentially. So there you're almost always either going to use the ratio test or the root test. In this case, I could also do it by geometric series consideration, but let's just stick with the root test. It's just as easy once we get used to it. So I'll use the root test because every factor of this sequence has an nth power, so the root test is a little bit easier than the ratio test. Both would work in this case, but I'll just do the root test. So the root test, we look at the limit as n goes to infinity of the nth root of the absolute value of our expression. So nth root is going to cancel our exponents. So we'll have the limit as n goes to infinity of absolute value of x plus 3 over 4. So the limit of that, there's no more n's, so if I'm taking the limit of this, I just get absolute value of x plus 3 over 4. Because there's no n's left. This is just a constant as far as n's concerned. Okay, so then to have convergence, to have a successful root test, I need this to be less than 1. So I need absolute value of x plus 3 divided by 4 to be less than 1. Well, then what you'll want to do is, I want to basically get x plus 3 by itself. So I'll show you why, but let's multiply both sides by 4. Okay, so look at what we have here. I basically have my parenthetical expression for my series, that is the x plus a number or x minus a number. I have that part less than a number. When I'm in that situation, this number is my radius. So this is r. So the radius of convergence is 4. Because if I want to solve this for x now, I can keep going, but if I solve this for x, I would say, well, how do you deal with an absolute value inequality? Your absolute value is less than 4 if the number inside the absolute value, x plus 3, is between positive 4 and negative 4. Well, then if I solve this for x by subtracting 3 from everything, I'll get negative 7 is less than x is less than 1. Okay, so then this is an interval, negative 7 to 1. Let me fit this someplace. Don't need all the root test stuff anymore. So my interval is going to be negative 7 to 1. And right in the middle of that interval is negative 3. There's a total distance of 8 between these two x values. Halfway through it, I'd add 4 to negative 7, and that gives me negative 3. I add 4 again to get to 1. So 4 is half the size of this interval. So that's this. That's the radius. Okay, so you don't have to write it out this way every time. You can just get to the part where you've gotten the inequality and you've solved it for the x minus a part, the parenthetical expression from your power series, the x part. If that's less than a number for your condition, that number is your radius. That is your r value. And then to figure out what your endpoints, you just take your center, -3, and add or subtract this number. So let me show you there. My interval is going to be -3 minus 4 to -3 plus 4. And that's -7 to +1. So -7 and +1. That's basically my interval, but I'll put parentheses for the moment, but we still have to check those two endpoints separately. Let me erase this. So now I have to check the endpoints. Because the endpoints, the endpoint x values are the x values for which my root test would have been inconclusive. So I have to check those with some different test. Most of the time, I mean, you're just plugging in the x value and you're going to see what kind of series it turns into. It'll usually be a p series or a geometric series or a p series or a alternating p series. Ones that we have quick rules for. So if I plug in, let me write that down, x equals -7, my series would be, let me not write this stuff every single time, -7 plus 3 would give me -4 to the n, divided by 4 to the n. And then if I simplify that, the 4's cancel, the 4 to the n's cancel, I'm just left with -1 to the n. So I'm -1 plus 1, -1 plus 1, -1. That doesn't converge. That's a geometric series where the r has absolute value 1. So this is a divergent geometric series. If I plug in x equals 1, then my series will become summation of 1 plus 3 is 4 to the n, divided by 4 to the n. 4 to the n divided by 4 to the n is just 1. Or 1 to the n if you want to think of it like that. Anyway, that's divergent. I guess you could also say both these are divergent by the divergence test. The limit of the inside is not 0, so it's divergent. Okay, so this time I got divergent at both endpoints, so I leave it this way. I leave my interval as being open, having the round parentheses, because neither endpoint is part of the convergence interval. Neither endpoint is part of the domain. The series does not give me a value when I plug in these two specific x values. All right? So let's do a couple more. So again, all these examples, it's the same question. Find the radius and the interval of convergence. Let's see. So n equals 0 to infinity, x to the n over n factorial. Okay, so I recommend just, at least at the beginning, taking note of what the center is, the center x value. Well, if it's just x to the n, the center is 0. So whatever your interval ends up being, its center should be 0 in this case. All right. So now we do a convergence test, either ratio or root. Factorials tell us ratio is probably much, much easier. So let's do the ratio test. With the limit of the absolute value of x to the n plus 1 divided by n plus 1 factorial. That's the n plus first term times the reciprocal of the nth term. It's n factorial divided by x to the n. So now if we simplify, the x's, there's one extra x on the top, so I have an x left over when I cancel. For the factorial stuff, n plus 1 has one extra factor that n factorial doesn't, so when I cancel, I'm left with n plus 1. So it's the limit of x over n plus 1 as n grows to infinity. Now this is easily to get confused. As far as this limit is concerned, x is fixed. N's the only thing that's changing. So if n is growing to infinity, I have a constant divided by infinity. That's 0. A number divided by infinity, that's 0. So then the question is, when is this convergent? Well, ratio test tells you convergent if your answer is less than 1. 0 is less than 1. So this tells us this is definitely convergent. It doesn't matter what x is. This is convergent anyway. Before, the last two examples, we got to a point where we got an answer that involves x, and then we need that answer to be less than 1, so we have an inequality that we have to solve for x, essentially. Here, I get a definite answer of 0. 0 is always less than 1, no matter what x was. So this is convergent no matter what. And that tells me x is irrelevant. My series is convergent always. So this is always convergent. So the answer to our two specific questions, what is the radius of convergence? It would be infinite. And the interval of convergence would be all real numbers, so negative infinity to positive infinity if I want to write as an interval. Okay, so that's an example where we have an infinite radius of convergence. If I had something like n to the n times x minus 5 to the n. Let's see, I guess if it's n to the n, I can't have n equals 0. That's undefined. So start with 1. It doesn't affect anything about convergence considerations. But the center for this would be 5. Because it's x minus 5. All right, so this one, again, we start by either picking the ratio test or the root test. This time, since I have an exponential part where n is both in the base and the exponent, that suggests I probably prefer the root test. So we take the nth root of this thing. Taking the nth root is just going to cancel these n's and divide each exponent by n. That gives me the limit of absolute value n times x minus 5 as n goes to infinity. Now this, again, x is not changing. X is fixed. The only thing that's changing is n. Well, as n increases toward infinity, that's infinity times a number, infinity times a fixed number. That'll be infinite, except if that number is 0, that doesn't really matter about n. If this number was 0, I would just have 0 for every single value in this limit. So it'd be the limit of 0, 0, 0, 0, and that's always 0. So this answer is going to be 0 if x minus 5 is 0. That happens if x equals 5. And it's infinite because it's absolute value, so it's going to end up being positive infinity no matter what. If x is not 0. Sorry, x is not 5. It limits infinity if x doesn't equal 5, because then this x minus 5 is some non-zero constant, and as n grows to infinity, that's going to grow to infinity. This absolute value stuff is going to grow to infinity. Okay, so these are the only two possible outcomes for this limit. We have convergent if the limit is less than 1. Infinity is not less than 1. 0 is. So the only time this is convergent is if x equals 5. So my radius of convergence would be 0. And my interval, well, it's not actually an interval in this case. It's just a single point. So it wouldn't be interval. It would just be a set of the single number x equals 5. So it's convergent at 5 and nowhere else. That's what that means. All right, let's do one more, and then I'll finish this section. Okay, so negative 2 to the n over n squared times x minus 1 to the n. And I guess I have to start at n equals 1 to infinity. Why don't you try pausing the video for a second, try to do this one on your own, and then unpause it and come back and watch me do it to check yourself. All right, so the center here is 1. Here, I could do the root test. The n squared would give me a little bit of a problem, and it wouldn't be an insurmountable one, but ratio test is like our default. And unless the root test is clearly easier, ratio test should generally be our default for these. So we look at the limit as n approaches infinity of absolute value of negative 2 to the n plus 1 times x minus 1 to the n plus 1 divided by n plus 1 squared. That's our n plus first term, times the reciprocal, which means n squared is on top, and these other things are on the bottom, so negative 2 to the n, x minus 1 to the n. Then we cancel. Negative 2, there's one extra negative 2 on the top, and one extra x minus 1 on the top. Then I've got, let me put them here, n squared over n plus 1 squared. So that's n over n plus 1 squared. And like we talked about when we did the ratio test originally, these rational parts, the polynomial parts from your series, when you do the ratio test with that, you end up with these fractions that it's the same degree on the top and the bottom with the same leading coefficient. So that thing's always going to approach 1. So this is 1 squared. So my limit's going to be, this part's 1, negative 2 times x minus 1, all inside the absolute value. So I can write this, absolute value of negative 2 is positive 2. Absolute value of x minus 1. Okay, so for my ratio test, I got this as my limit. 2 times absolute value of x minus 1. So then I need that to be less than 1. To have a successful ratio test, I need that to be less than 1. So then what you want to do is solve for the parenthetical expression from your series. In this case is x minus 1, so I want to divide by 2. I need x minus 1 absolute value to be less than 1/2. So at that stage, that tells me the radius r is 1/2. Okay, so then to get my interval, I don't know I have to check endpoints, but let's write the interval first. I take my center, 1, and I add or subtract the radius. So 1 minus 1/2 would be 1/2. 1 plus 1/2 would be 3/2. So these are my endpoints. Now I need to check them separately. So I'm going to plug these in for x and then simplify my series. So let's do x equals 3/2. My series would become negative 2 to the n over n squared. 3/2 minus 1 to the n. I'll just simplify it as I write it. So 3/2 minus 1 is 1/2. Now if I simplify that, negative 2 to the n on top divided by 2 to the n on the bottom, that's going to leave me with negative 1 to the n over n squared. That's an alternating p series with p equals 2. That's convergent. So that tells me when x equals 3/2, I get a convergent series, so 3/2 should be part of my interval. Right? And then doing the same thing, if I plug in x equals 1/2, 1/2 minus 1 is negative 1/2. So now the 2's cancel, but so do the minus signs. Now I just get 1 over n squared. That's an ordinary p series with p equals 2. For that, p just has to be bigger than 1. This is still convergent. So x equals 1/2 also worked, so we also include it in our interval of convergence. So our radius is 1/2, our interval is 1/2 to 3/2. 1 is right in the center of that, and we included both endpoints for this one. All right, so we finished 11.8. I will put up a list of problems at the end of this video. The next couple sections we will be looking at how do we use power series to represent certain kinds of functions and what those power series representations can do for us. All right, I'll stop there.